Okay, so in this video we're going to start topic 5.1. Um, so topic 5 overall is called electricity and magnetism, and here you can basically see the different subunits within topic 5. We have 5.1, we have 5.2, 5.3, and then 5.4. So this unit we're starting today is only going to be over 5.1. The next unit, which covers circuits, is going to cover 5.2 plus 5.3, and then 5.4 will be its own unit. Now, I'm just going to warn you now that this topic is probably going to take up the rest of the semester and probably spill over into the next semester as well. And in my opinion, this topic 5 is probably the most difficult topic in all of IB physics, just because it is a very abstract topic. There's a lot of things that we'll be talking about that you cannot physically see with your eyes, and there's also some math involved in some of these topics that are kind of difficult to deal with. And so I will do my best to explain these concepts to you, but I would always encourage you to seek out your own resources. Use the IB Physics textbook. The Walter Lewin videos that you can find on YouTube are really good for electricity and magnetism, although if you watch some of those videos on YouTube, do understand that that is a calculus-based class, and so some of those concepts are covered in a lot more detail than you need to know for this class. Okay, so just to kind of introduce you to 5.1. 5.1 is called electric fields, and so some of the things we'll be talking about are charge, electric field, Coulomb's law, electric current and direct current. We'll talk more about that in the next unit, but we will also talk about potential difference in 5.1. As far as what you must be able to do in this unit, you must be able to identify two forms of charge and the direction of the force between them, which is pretty simple. You must be able to solve problems involving electric fields and Coulomb's law, which I think is kind of ambiguous because it doesn't say what type of problems, and there's lots of different types of problems you could see with those things. So we'll do our best to cover all of the types of problems that you might see on the IB exam. Calculating work done in an electric field in both joules and electron volts. Identifying sign and nature of charge carriers in a metal. Identifying drift speed of charge carriers, solving problems using the drift speed equation, and then solving problems involving current potential difference in charge, which again is kind of ambiguous because you could see lots of different problems involving this concept. So we'll see what we can do. You are given quite a few equations in this in 5.1. Under guidance, it says that students will be expected to apply Coulomb's law for a range of permittivity values. I think I'll talk about that in the next video, but that is something you should be aware of. And as you can see, you have a host of different equations given to you in the data booklet, and as we go through the unit, we'll go over most of these. Okay, we might talk about current in the next unit, but we'll kind of see how things are going. But most of these equations we'll definitely get to. Okay, so in this video, we're going to start off pretty simple, and we're going to start with this concept of charge. Okay, so this is where the notes begin. And some of this you might have heard already in the Walter Lewin video, but it's been known for centuries that some objects have a property which we call charge. And even going back to the Greeks, they had noticed that if you rub amber, which is like fossilized tree sap, I believe, with different types of animal fur, that after a while you can actually see a spark. And in the Walter Lewin video, he talked about how the women would do that with their jewelry, and they would touch frogs, and the frogs would jump as they would get a shock. And so actually that's where the word electron gets its name from. Electron is the Greek word for amber. So that's where that comes from. And so through a variety of different types of experiments, it has basically been discovered, or had been discovered, hundreds of years ago, that there's basically two types of charge. There's what's now called positive charge, and the other type of charge is negative charge. Okay, so let's talk about some of the properties of charge. Now, of course, we know that in the basic model of an atom, you have, a positively charged nucleus, and then you have electrons kind of on the outside of the atom. At least, in the Rutherford model and later models of the atom, that's what you have. Now, as long as you have an equal amount of positive and negative charge, you have what's called a neutral situation. So if you have an atom that has an equal amount of protons and electrons, we would say that atom is neutral, because proton has a positive charge and electron has a negative charge. And so if you were to take a neutral atom, if you take an electron off of that atom would become a positive ion, which would be called a cation. And so that atom would be positively charged. And if you add an extra electron to an atom, you get what's called an anion, which is a negative ion, or a negatively charged particle. And I'm not going to go too much into the chemistry of, how that works and which atoms can accept how many electrons. It's not important for this class. But essentially how an object becomes charged has to do with it gaining or losing electrons. And so that's kind of what we're going to be focusing on. Now, before we talk, let's talk about some properties of charge. So this would be excellent to add to your notes. Okay, so first of all, the symbol for charge is typically written as a lowercase q. Although you can write it as an uppercase q, it doesn't really matter. Charge is a scalar. And the SI unit for charge is named after a French physicist who did a lot of experiments with electricity, and his name was Coulomb. And I say it like that because he was French. So don't say Coulomb or anything weird like that. You would pronounce the name Coulomb. And the way you write that is with a capital C because it's named after a guy. We capitalize that letter. Just like for Newton, you write a capital N for Newton. Now, 1 coulomb is an enormous amount of charge. You would typically never see that much charge actually, because it really is a massive amount of charge. If you think about the amount of charge in like a bolt of lightning, you're probably talking about somewhere between 10 and 50 coulomb, and that's in a lightning strike. So 1 coulomb is a massive amount of charge. It's most likely that you'll see problems involving nano or micro or millicoulomb, sometimes smaller, sometimes larger, but usually really small units of charge for calculations. And so make sure you're keeping in mind your SI prefixes as you're doing problems with charge. Now, after many, many decades of careful observations, scientists reached the following conclusions about charged objects. Okay, so conclusion number 1, there's 2 types of charge, which we now call positive and negative. Observation number 2, if you have 2 objects and they both have the same type of charge, those objects are going to repel each other. There's going to be a repulsive force between those objects. If they have opposite types of charge, then those objects attract. So in other words, positive and positive repel, negative and negative repel, but positive and negative attract. And so if you've ever heard the expression opposites attract, that's where that comes from. And then 3, the amount of repulsion, the amount of force, or I should also say the amount of attraction. It could be attracting force, but it depends on the distance between the objects. And so the closer the 2 objects are to each other, the greater that force that they experience. Once we discovered electrons, it was eventually discovered after that objects that have a negative charge, the reason that they have a negative charge is because they tend to have more electrons than protons. And objects with a positive charge, it's not that they've gained extra protons, it's that they have lost some electrons. And so if you think of the model of the atom with the electrons on the outside and the positive charge is contained in that nucleus at the center of the atom, it's held together by the strong interaction because of the neutrons and the quarks attract each other, gluons and all that other stuff. And so really what can change in an atom is the number of electrons. Either you gain electrons and you become negatively charged, or atoms can lose electrons and become positively charged. Okay, now we've talked about how protons have a charge of +1 and electrons have a charge of -1. You might have heard that before in chemistry, but you might not be aware of what that means exactly. Okay, so +1 what, or -1 what? And so it turns out that when we say a proton has a charge of +1, what we mean really is we mean +1e, or 1e. So what is an e? Well, 1e is what's called the elementary charge, and the value for e is approximately equal to 1.6 times 10 to the -19 Coulomb. Okay, so a proton in terms of Coulomb has a charge of positive 1.6 times 10 to the negative 19 Coulomb, and an electron has a charge of negative 1.6 times 10 to the negative 19 Coulomb. And so the reason we use the elementary charge is that's just kind of the base, not basing, but it turns out that the smallest amount of charge you could possibly have is actually that amount. And so that's why we write the charge of the proton and electron in terms of the elementary charge. And that value is given to you in the data booklet, by the way, okay, the elementary charge. Okay, so moving on. Okay, so we know everything is made of atoms, but we can also classify different types of objects and materials by whether or not they're conducting or non-conducting. And so in very simple terms, a conductor, which, when you think conductor, think metals, a conductor is classified as a conductor because those types of materials have what's called free electrons, okay, loosely bound electrons. And what I mean is, if you think of like, let's say a metal atom, it has electrons, of course, surrounding the nucleus, but a small amount of the electrons on the very outside of the atom are not super tightly bound to that nucleus, which means they can very easily fall off the atom and go do other stuff. And so, because metal atoms tend to have this property, metals are classified as conductors, meaning they can easily conduct electricity because those free electrons, because they're not tightly bound to the atoms, they're free to move, and so they can respond very easily to electrical forces. Whereas in an insulator, like plastics are a great example of an insulator. Wood, glass, rubber, those are all insulators. The electrons are tightly bound to the atoms, and so it's very difficult to move those, and so they don't conduct electricity very well. By the way, this is kind of random, but just a fun fact. Pure deionized water is actually a very good insulator. And most people, when they think of water as being conductive. But that's because most water contains some amount of salt. And salts are, basically ionic compounds. And so when you put them in water, they dissociate. And it's the ions that are conductive because they can conduct electricity rather than the water itself. And so pure water, like deionized water that you can buy at the store, is actually a very good insulator. Anyway, so moving on past that, let's talk more about this charge. And Walter Learn kind of talked about this in his video, but you can do some basic experiments to demonstrate the creation of charges. And when I say creation, I put it in quotation marks because you're not actually creating charge, as we'll see. But if you were to take a rubber balloon and you rub it on a piece of wool, basically what happens is through that act of rubbing, the balloon strips electrons off of the wool. Okay, that means the wool atoms have lost electrons, and those electrons are now on the balloon. And so what that means is that the wool, because it has a deficiency of electrons, it now has a positive charge, and the balloon, because now it has more electrons than normal, now has a negative charge. And so actually the balloon is going to stick to the wool. Now understand that we have not actually created any new charge. Okay, the wool and the balloon were both electrically neutral. Now one is positive and the other is negative, but the overall net charge is still 0. All we've basically done is we've transferred electrons from one object to another. Okay, and so now what's going to happen is the wool and the balloon are actually going to stick together. And you might have observed this phenomenon if you've ever taken a balloon. If you rub it on yourself, you can get the balloon to stick to your clothes or stick to your hair, and that's basically why that happens. Okay, the act of rubbing, that friction, causes electrons to be forcefully removed from one object and placed on another object. Okay, and so if you were to do this with two different balloons, and you place the two balloons close to each other, you would find that those balloons actually repel. And so that's a simple demonstration you can do to find out that, hey, if I have two objects that have the same type of charge, in this case both have a negative charge, they are going to repel. Okay, but of course the balloon and the wool, one has a positive charge, one has a negative charge, and so those are going to attract each other. Okay, this right here is just a little animation showing the difference between a conductor and an insulator. On the left side, you can see a rod comes in that has already been charged, and in a conductor you have these free electrons, and so you can see the negative charges in the conductor move all the way across the whole object to be close to that charged rod. Whereas on the right side, in the insulator, the electrons in the insulator atoms can kind of shift around a little bit, but they're still tightly held to their atoms, and so that they shift a little bit, but they don't move around completely. All right, so let's see. We've talked about objects that are charged having too many or not enough electrons before. I think we've talked about this before. We've talked about how protons and neutrons are kind of buried deep inside the nucleus, and so you don't charge an object by adding protons to it or removing protons from it, because those protons are locked up inside that nucleus. But the electrons orbiting the nucleus can easily be gained or lost, depending on what type of atom it is, of course. Okay, now through lots of different demonstrations, basically it's been discovered that you cannot actually create or destroy charge. And so we've talked about conservation laws before. In fact, we've talked about this conservation law before. But there is a conservation law called the conservation of charge that basically says that charge cannot be created nor destroyed. And so this is one of the fundamental conservation laws of the universe. And some, conservation of energy, conservation of momentum, things like that. Just one of the fundamental conservation laws in the universe. And so anytime you're charging an object, if you charge up one object, that means another object is losing that charge to begin with, because the overall amount of charge in a given situation cannot be changed overall. Okay, so usually when we talk about something becoming charged, let's say something gains a positive charge, that means something else had to have gained an equal amount of negative charge to compensate for that. All right, so let's just do a simple example. Let's say we have Albert the cat, and this question says, a cat's fur, like your hair, acts just like wool when you rub a balloon on it. A balloon has picked up 150. Remember what the symbol is. This is the Greek letter mu, so this is micro. So 150 microcoulomb of charge from Albert. The resulting opposite charges of balloon, and Albert caused the balloon to stick. By the way, you can actually do this demonstration at home. If you take a balloon and you rub it on a cat, the balloon will actually stick to the cat. And the first question says, how many electrons have been transferred? And so to answer this question, the way you would approach it is you would say, okay, so one electron has a charge of negative 1.6 times 10 to the negative 19 coulomb, okay, which is a very small amount of charge. And we basically want to know how many electrons does it take to make up 150 microcoulomb of charge. And so the way we would do that is we would just take 150 microcoulomb, which is 150 times 10 to the negative 6 coulomb, and divide by the elementary charge. And if you do that, you can see the answer on the slide here. You get a very large number, 9.4 times 10 to the 14 electrons have been transferred in this situation. So the balloon has gained what sounds like a small amount of charge, right? Only 150 microcoulomb. But the amount of electrons that had to be transferred for that to happen is actually a ginormous amount. Notice, by the way, that before you rub the balloon on Albert, the overall charge in the situation was 0. And so if the balloon has gained 150 microcoulomb from Albert, the net charge in the situation must still be 0. So if the balloon is now positively charged, that means it lost electrons. That same number of electrons must be on Albert the cat. Okay, which means that the charge of Albert now has to be negative 150 microcoulomb. And so that's what you see here down at the bottom. Okay, remember the symbol for charge is a Q. Okay, so Q Albert, that's the charge on Albert the cat, is negative 150 microcoulomb. Okay, so pause it there if you need to add that to your notes. Okay, so the last thing I want to mention in this video is basically about an object called an electroscope. Okay, and this is something that you don't often see, but sometimes shows up on IB problems. So I thought I would show you at least what it looks like. Okay, and so an electroscope is basically a device that looks like this. I have a version in my classroom, which I wish I could show you. But basically, the purpose of an electroscope is to detect electrical charge, and it's a very primitive instrument that was used hundreds of years ago. But essentially the way it works is you have a glass flask with a rubber stopper that has a hole in it, and through that hole you have a metal rod that you can see here. Okay, now at the bottom of the rod you have these two thin pieces of metal, and those are called leaves, like leaf. If you look on the slide, it says, you know, a very thin and flexible gold leaf. The one I have at school does not have gold in it. It's aluminum, and so the two pieces of metal are actually aluminum. Any conductor would work, but you know, it would be nice if it was gold. But the important thing is that it's a conductor. Okay, and so here's how the electroscope works. Actually, let me draw this. Okay, so let's say the electroscope is electrically neutral, meaning you have an equal amount of positive and negative charge. Okay, so let's say you have, you know, some positives. Actually, let me just go forward a little bit. Okay, so let's say we have positive charge. So positive, positive, negative, negative, positive, positive, negative, negative. So let's say this whole thing is electrically neutral. Positive, negative, negative, positive, whatever. Equal amount of positive and negative charge. But let's say, hypothetically speaking, that we took something that was already charged, let's say like a rod, we rubbed it with wool or something, and let's say we made it positively charged. Now what's going to happen is, inside the conductor, remember you have free electrons that are free to move, and so what's going to happen is, if this rod that's close but not touching the electroscope, if this has a positive charge, the electrons in this metal rod are going to be attracted to this rod up here. So what's going to happen is the free electrons, not all of them, but you know, many of them, are going to kind of migrate up to the top up here because they are attracted to this positively charged rod. Okay, but because of conservation of charge, if the free electrons drift up to the top, that means they leave behind these you know, positively charged nuclei that lose some of their electrons. Not all of their electrons, by the way. When I talk about free electrons, I'm talking about like a very, very small fraction of the overall number of electrons. And so I don't want you to think, you know, if there's 30 electrons on an atom, that they don't all fly off. I'm talking about, you know, maybe like one electron out of like 30 or 40 or 50 attached to a single atom. And so this effect is not like, you know, crazy big or anything, but it's enough to detect. In any case, let's say the free electrons kind of migrate up to the top, leave behind positively charged atoms. So what happens is these metal leaves at the bottom, if they both become positively charged, those leaves are going to repel because, you know, positive and positive repel. And so if you do this experiment, you can actually see the leaves spread apart, and so this device is used to measure the existence of electrical charge. The more charge you have, the more the leaves repel apart, because that means that the forces between the leaves are greater. And so on the next slide, you can kind of see what this looks like. Here we basically have a situation where it's asking, you know, which one has the greatest charge in the leaves and which one has the least. The one with the greatest amount of charge is going to be spread apart the most. And so here you can see, looking at these three electroscopes, this one shows the greatest amount of charge. You can see the leaves are really spread apart because they're repelling each other really hard. The least amount of charge is going to be the middle one. But the last question says, can you tell whether or not the charge is positive or negative? And the answer is no. You cannot use an electroscope to determine whether or not you have positive or negative charge, because in the example I gave before, I used a positively charged rod, and I said that the free electrons are attracted up towards the positively charged rod. But if I had replaced that with a negatively charged rod, then what would happen is, just to go back to the last slide, if you had a negatively charged rod, let's say, I don't want you to think that the positive charge would drift up to the top, because that's not what would happen. Remember, it's not positive charge that typically moves, it's negative charge, because those electrons are typically free to move. So if you did have a negatively charged rod, then the free electrons in this metal down here would be pushed down towards the bottom. The bottom would gain an overall negative charge. The top bit would become positively charged because, the electrons that used to be there are no longer there. And so if the leaves at the bottom become negatively charged, the same thing is going to happen. They're going to repel each other because negative repels negative, and they're going to spread apart. So again, what is the purpose of all this? Basically just to detect the existence of charge. You can't tell what type of charge you have, but you can at least, qualitatively do a demonstration where you see whether or not an object is charged by bringing it close to the electroscope. Okay, so we're going to stop the video there. In the next video, we're going to start talking more quantitatively about the force between electrical charges, and that's going to involve what's called Coulomb's law. As always, please let me know if you have any questions, and I'll see you guys in the next video.